Okay, so for this this video, we're going to be looking at how to sketch logarithmic graphs. Just like their cousins, exponentials, they are one-to-one functions and they have the form written there. This little value of a down here is, of course, the base of the logarithm, and all the others, a, b, and c, and d, are all transformations of some kind. So let's have a look at what is what. This value of a is dilation factor from the x-axis, stretching it up or squishing it down. And if it is negative, it gives you a reflection around that same axis, the x-axis. This value of b, this thing here is a dilation factor of 1 over b from the y-axis, and it will give you a reflection around or about the y-axis. So the y-axis becomes a mirror for it. This d at the end, this is our vertical translation. Not an asymptote in this case. The asymptote applies to the vertical component in this time, and that's where the b plus c is helpful. This bx plus c, if we solve it equal to 0, that will give us the horizontal translation. And it will also give me the vertical asymptote. So whatever makes the inside of the logarithm 0, this bit in here, that is your vertical asymptote. Now the general shape is over here on the left. This is an inverse of an exponential graph. So an inverse an exponential graph would have had a horizontal asymptote. In the inverse, it becomes a vertical asymptote. It would have had a graph that goes through the y-intercept, which now becomes the x-intercept, and will move away from the x-axis, whereas a logarithm will move away from the y-axis in this drawing. So it's an inverse of the exponential. Remember, inverses, of course, are reflections around the mirror of y equals x. Go look at the other video to remind you of that. The maximum domain is always one side or the other one. We're not dealing with modular signs here. We're only dealing, the way I'm speaking at the moment, I'm dealing with logarithm graphs with a linear term inside the logarithm. I guess that's important to note because it can be different with other things in there. But the linear term inside the logarithm, we can only have one side of the asymptote unless we have absolute value signs, which is not in the course we're looking at. So it's x is bigger than the asymptote. It's always bigger than if b is bigger than 0, because this is the way the graph goes if b is positive. It'll be everything on this side if b is negative, because negative reflects it around that y-axis and goes the other way. And unless it's restricted, it'll have a range of all real values. So with all that in mind, let's sketch the following 3 graphs. And I'll come back to the domain and range at the end. So first thing, vertical asymptote. Well, you can see the bit inside the bracket is x minus 4. So you end up with x equals 4. Now that shouldn't say t, that should say a, vertical asymptote. 1 is a vertical translation, but that's not going to help me at all sketch this thing. So x equals 4 is all the way over here. So it's going to be a really unhelpful way to draw this graph, but too late. F of 0 is not going to be valid because notice what happens. Log base 2 of 0 minus 4 plus 1, that is negative. You cannot have negative inside a log, so this just means there's no x-intercept. Well, no y-intercept, sorry. Sorry, wrong one. No y-intercept in this case, because y-intercepts would be something like this, but we're actually drawing a graph that's going to go this way. So to find the x-intercept, let's solve this thing equal to 0. We subtract 1, we times by 2. Remember, to undo a logarithm, it's to this base 2 to the power of -2 equals x take 4. So x equals 4 plus, or 2 to the -2 can be written as 1 over 2 squared. So really it's just 4 1/4. That looks like a power. It's not supposed to look like a power. It's supposed to be next to it. 4 1/4, which is 17 over 4, which is going to be about there. So really we're looking at the graph, it's coming pretty much vertical, almost vertical, not quite, to there, and then it's going to curve over and start going away like that. To get coordinates for accuracy, it's always a good idea to substitute values in. So for example, we could substitute, while I make this 17 look worse, you could always substitute x equals 5 in to the logarithm. 5 minus 4 is 1. Log base 2 of 1 is 0. So when x is 5, you'll end up with 1 there. Coordinate of 1 and 5. You don't have to label 5 1, but it's good to help you get some accuracy when you're drawing. The next one. This one's gonna be a little bit nicer to sketch as a translation to the left rather than to the right. So that will mean I'll actually be able to get it on the axes. So again, we're going to have our vertical asymptote. It's going to be whatever makes the logarithm 0 on the inside, which it does not appreciate, is x minus 2. So we're going to have x minus 2 marked all through here as our vertical asymptote. Did I label that one? I didn't. You need to label your asymptotes. Next one, we're going to try to find our y-intercept. So g of 0 equals 3 log base 2 of 0 plus 2 minus 3. Now, log base 2 of 2, this is equal to 1. 2 to the power of what gives you 2? Oh, that's 1. So that's 3 times 1 minus 3 is 0. So we actually have our y-intercept is there, which actually means that is also our x-intercept. So I'm not going to bother trying to find an x-intercept, we already know it. So I know it's going to have to be, it's a positive there, it's a positive there. So it's going to be coming up through there and coming out. To get some kind of precision, I guess, accurate, let's substitute a value and let's try g of -1. Now I'm choosing -1 because nice inside a logarithm, you get 3 log base 2 of -1 plus 2 minus 3. Now it's nice in a logarithm because 2 minus 1 is 1. And anytime you have log base of anything of 1, it drops out to be 0. So 3 times 0 disappears, you get -3. So -1, -3 must be coming up through that. And I'm going to find the next value that's going to give me a good value to find logarithm of. That's going to be 2 in this case, because we're dealing with base of 2. So if you have log of 1, the answer is 0. If you have log base 2 of 2, you get 1. Log base 2 of 4 is going to be 2. We're dealing with bases of 2. So you want to have 1, 2, 4, 8 or something here, make it nice. But in this case, it's a 4. Log base 2 of 4, or 2 to the power of what gives you 4? It's 2. So it's 3 times 2 minus 3, which gives you 3. So when you have x equals 2, you're going to have 3 there. So I'm going to come up through here. And it's going to really start to shape around like that. Again, with this in here, heading towards that asymptote. Down the bottom down there, I'm just going to eraser and tidy it up a little bit down here. Want to make sure it's as tidy as you can when you're sketching for exams and things. Even this little bit's here, not greatest. You'd get an eraser and just work on that to fix it a little bit. I won't, because I'll lose my whole line. Final one, same idea. You're going to have vertical asymptote first. 6 minus 2x equals 0. The other two you could see straight away what the asymptote was. But if you get in the habit of thinking put the bit inside equal to 0, you can deal with any asymptote thrown your way. And you got x equals 3, which is going to be down here. Remembering always that the vertical asymptote is x equals. We have a negative 2x this time, which means the graph is actually going to be coming from the left-hand side. And a positive 2, so it's still going to be coming from up there. So we are going to have a y-intercept this time. So we have 2 log base 3 of 6 minus 2 times 0 minus 4. In this case, unlike the other ones, we don't have a nice logarithm of 6. So you're going to have it as an exact value. If you've got a calculator, you can get a decimal value, but we're going to have an exact value in this case. We don't actually know what that is, but that's all right. So that is going to be our y-intercept. We'll label that in a minute. And to find the x-intercept, we're going to substitute 0 in for y, just as normal. So to solve this, we're going to add 4, divide by 2. Whoops, that should be 6 minus 2x. To undo the logarithm, remember, is 3 squared, which is 9 equals 6 take 2x. Subtract 6 gives you 3. That's 9, take 6 is 3. Divide by negative 2 is negative 3 on 2. So negative 3 on 2 is there, which means this logarithm 2 log 3 of 6 minus 4 is down here somewhere. That'll be a long way down. But to help with some accuracy, I want to get some more coordinates because I don't know what the value of this thing is. This really is one of the, I don't know what it is. I know it's going to be somewhere between -1 and 0, I reckon, but why don't we try to find some values that when we put it into here is going to give us a nice base that we can work with. All right, so just like with the 2, we had 1, 2, 4, 8, 16. We want to do the same with 3s. You want 1, you want 3, you want 9. Those sort of ones. So let's think about it. So what value needs to go into 6 minus 2x so that I have a value of 1? Well, the answer is 5 over 2. If I have x is 5 over 2, 2 times 5 over 2 will give you 5. 6 minus 5 is 1. That's a good thing. So let's try h of 5 over 2. That's going to give me 2 log base 3 of 6 take 5 over 2 times 2 take 4. Now, we just said this thing gives you 1. Log base 3 of 1 is 0, so you end up with -4. So next is 5 over 2 there. You have -4 there. So it's got to go through there. I'm going to do the same thing with other values. This time I want to make it a 3 there. What number should go in there to make it 3? Well, that's going to be, so I'll make it 3. That'd be 3 over 2. Because 6 minus 3. Okay, so 2x must be 3 over 3 over 2. Let's do the same thing, but in this time, making this one a 3. I hope my logic is making sense as we go through here. So 6 minus 2 times 3 over 2. 2 is cancelled. 6 minus 3, 3. Log base 3 of 3 is 1. Times it by 2 is 2. You get -2. So 3 goes in there. So 1.5 there ends you at -2 about there. And the other one that would be useful to us would be 9. But to get 9, you want x being a negative value, which is what we had before. That was this thing down here. That's our x-intercept. So it's going through these 3 points and it's going to come up and out. So we'll do our best. So I'm going to come through something like, sorry, come up through there. You think of drawing on a little drawing pad. It's not the same as moving a piece of paper. Something like that. Now, on an exam, of course, you would try to tidy up those little kinks, but that's the general idea of it. And in there, you're going to have your -4 log base 3 of 6 and 0. Oh, I thought the 2. And that is your graph of a log. It's not a very nice one, but it's doable. Last thing, we want domain and range of each one. So the domain of each one, or domain of the first one, is bigger than 4. We can see that. And the range is no restriction. So it's going to be all real values for y. The domain of this one, well, it's everything bigger than -2, because that is our asymptote. And again, there's no restriction, so the range is again going to be y is all real values. And the final one is going the other way, this one. So your domain this time is going to be less than 3, with the range again being all real values because there's no restriction on the domain. But check for restrictions on your domain. And that is how you sketch logarithmic graphs.